Test day is like game day. LeBron James does not deliver on natural talent alone. He puts in many hours of practice each week, thousands of repetitions, conditioning, drills, practice shots. Success on graded review game day requires correctly practicing at least 50 practice problems from the assigned homework. Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. Today we're having a look at section 12.2, number 32. And we're going to use the problem-solving format with the mnemonic device IDEA that you may have used in other classes. And I stands for interpret or identify, D stands for develop, E stands for evaluate, and A stands for assess. Taking a structured problem-solving approach really helps when solving challenging problems like this one. So we start off with I, identify, and here we want to use the general principle in physics is equilibrium to compute the unknown tensions. And to develop, well, first we want to develop our picture a little more. And to develop our picture, we can recognize that the sum of the forces acting at this point have to be zero, because that's the equilibrium condition. So we have negative mg pulling down on the star. We have this tension, which we'll call T2. We'll call this one T1. And the idea is that tension 1, tension 2, and gravity all produce vector forces. So when we add the forces like vectors, the total force should be zero because the star is not accelerating. So we can further develop the idea by using the alternate interior angle theorem from geometry, which tells us that this has to be 52 degrees because these are alternate interior angles, as well as this has to be 40 degrees because these two are alternate interior angles. So we've improved our picture. So now let's make our plan. We want to compute T1x and T1y. Then we compute T2x and T2y. And you might be saying, wait a minute, if we had the magnitude of the tension, we could compute those using SOHCAHTOA or the ideas from physics about how you compute the components of a vector, but we don't have those magnitudes. Those magnitudes are the unknown. So you could say compute, but it might be better to say express. So we want to express in terms of the magnitude of T1 and the angle of T1. And then we can also express T2x and T2y in terms of T2 and theta 2. And then we can express, and let's call this down here the force of gravity. So we're expressing the x and y components of the force of gravity. All right, and now we want to set the sum of the x forces equal to 0, and we set the sum of the y forces equal to 0. And what this gives us is two equations and two unknowns, right? Our two unknowns are T1 and T2, and they're the only unknowns that should appear in these two equations. So now we can solve for our unknowns T1 and T2. All right, so we've identified our big idea. We've amended our picture and developed our plan, and now we need to start executing or evaluating our plan. So T1x is equal to T1 times the cosine of theta 1. And here we want to be careful because when using certain techniques to compute the components of a vector, you always want to measure that angle with respect to the positive x-axis. So if this is the plus x-axis and this is the y-axis, then theta 1 is the 40 degrees. So T, and oops, now we have to be careful here. We've gotten a little confused because this is T2, and so this would be T2x is equal to T2 times the cosine of theta 2, and T2y is equal to T2 times the sine of theta 2. Now, it was straightforward for T2 because this angle's with the positive x-axis. But we need to think about, well, what is theta 1? Theta 1's not this 52 degrees, but it's the angle here, which is 180 minus 52 degrees. So theta 1 is 128 degrees. So now we can write T1x is equal to T1 cosine theta 1, and T1y is equal to T1 times the sine of theta 1. And you will be well served both in Calc 3 as well as in physics if you resist the temptation to plug in numbers until you're a little further along and you absolutely have to. All right, now express the x component of gravity. Well, when you think about things here, the angle that the gravitational force is making is negative 90 or 270 degrees. And the cosine of that angle is 0. You could also tell by the picture that the x component is 0. And the y component is simply negative mg. All right, now when we sum the x forces, it's going to be 0, but what we're going to have is T2 cos theta 2 plus T1 cos theta 1 is equal to 0. And then when we sum the y forces, we have T2 sine theta 2 plus T1 sine theta 1 minus mg equals 0. So before we pursue the algebraic solution for T1 and T2, let's zoom out and see if this makes sense with our picture. And indeed it does, because what do we have here? Here we have T2 pulling to the right in the x direction, and it needs to be equal and opposite to T1. We're expecting, because theta 1 is 128 degrees, this cosine is going to be negative, and so they're kind of pulling in opposite directions. At least one's pulling in the positive x and one's pulling in the negative x direction, such that they balance out and they equal 0. In the y direction, both tensions are pulling upward, or positive y, and the gravity, minus mg, is pulling downward. So the upward tensions are holding the thing up and balancing the downward force of gravity. So now we can proceed to solve by the standard technique of substitution, because we have the two equations and two unknowns. And let me encourage you here to take a deep breath, because this is not the easiest substitution type of problem that you're ever going to encounter. All right, so we need to erase something here. Let's go ahead and erase our plan since we're to our last step in our plan. So let's call this our x equation and this our y equation. And let's solve the x equation for, say, t2. So t2 would be negative t1 cos theta 1 over cosine theta 2. And we arrived at this simply by subtracting this from both sides and then dividing both sides by theta 2. Now, by the technique of substitution, we can take this expression, which is equal to t2, and then we simply substitute it in there. So then the y equation gives us negative t1 cos theta 1 over cos theta 2 times sine theta 2. And then we add t1 sine theta 1. And let's go ahead and add the mg to both sides to make that equal to mg. And then you think, oh no, boy, that looks like alphabet soup. But we can proceed in an orderly way, and we can factor out the t1. And when we factor out a t1, we get t1 sine theta 1 minus cosine theta 1 over cosine theta 2 times sine theta 2, and all this is equal to mg. Now from here we should see our way clear pretty much to a solution, but we need to make a little more room first. Right, we can divide both sides by the term in parentheses, and we arrive at t1 is equal to sine, well, we're dividing everything by that term in parentheses, so t1 is equal to mg divided by, and now we're just rewriting the term in parentheses carefully, sine theta 1 minus cosine theta 1 over cosine theta 2 times sine theta 2. And the important thing to realize now is that everything on the right hand side of the equation, well, we've represented it symbolically, but they're just numbers that we know. This is the 10 kilograms. This is the acceleration of gravity, 9.8 meters per second squared. And these are the sines and cosines of angles that we know. So t1 then is just a number, and then t2 is equal to negative t1 cos theta 1 divided by cos theta 2. So we should see our way clear from here to the solution. Substitute in, solve for t1, substitute in, solve for t2. All right, now how are we going to assess? Well, some considerations when it comes time to assess is that T1 and T2 should be, T1 and T2 should be on the order of 10 kilograms times 9.8 meters per second squared, because this is the force pulling down, and if we have something, 10 or 100 times larger or 10 or 100 times smaller, we know we've made a careless error. So they should be in the ballpark of 980 newtons, and we set them up by definition that they should be positive. In addition to this assessment to see if things make sense, you can also plug them back into the original equations that we developed to set the x and y components of the net force equal to 0, and plugging them back into those equations and getting 0 would also be a powerful assessment technique. Well, this is a little embarrassing. The assessment that you saw a minute ago was incorrect. The ideas behind it were okay, in that the total ballpark of the tensions should be of the order of magnitude as the weight that's hanging on the wires. But a minute ago I multiplied 9.8 by 10 and came out with 980. Must have been thinking Arby's. Alright, of course 9.8 times 10 gives a ballpark answer of 98 newtons. This isn't an exact answer. The ones we worked out with the more complex method are the ones that we really want, but this is a number that you can compare them to in order to know what ballpark we're expecting the answer to be as an assessment method.